All right, guys, so we're going to go over really quickly Labflow number 6 compounds and their bonds. All right, so this one is mainly about breaking apart your chemical formulas, creating chemical formulas, looking at molecular structures, naming, and drawing Lewis dot structures. Some of this we've already gone through in our PowerPoint. Some of it we didn't really cover much, and we're going to cover that right now. So the first part is introductions to what is an ion, which we went over. An ion is basically an atom that has lost or gained an electron. So here in our example, right here, we could see the sodium atom. Sodium has one valence electron in its outer shell, and sodium is a metal. Metals tend to lose electrons, okay? So metals tend to lose their electrons. And as metal loses its electron, right, it loses that valence electron in its outer shell, you notice that the atom actually becomes smaller, okay? And the reason that's happening is because now it's talking about its second shell. So it lost its third shell, so now it's on its second shell, right? It went from a 1s to a 2s, 2p, 3s, all the way down to just a 2p. So it lost the third outer shell, making the atom smaller, a little bit tighter together. And now electrons are negatively charged. And what that means is if you lose something that's negative, you become more positive. So the way to think about this is in your life, if you hang out with like negative people, you're going to become negative. The more negative people that are around you, the more negative you're going to be. However, the more you lose negative people in your life, the more positive you're going to start to be, right? So if that negative influence leaves, you're going to be more optimistic, right? More happy. Um, and that's the case in this scenario. As the negative electron leaves, the atom becomes more positive, right? So here it is, it's more positive. And this is called the sodium ion. If we recall in our naming, when we name a metal ion, all we do is name the actual name of the metal, in this case sodium, and then just write the word ion. Um, Now, it's different when it comes to an anion, right? An anion is an atom that's gained electrons. This right here is a cation because it's positive, right? So cations are easy to name. It's just the metal in the word ion. Anions, they change the ending a little bit, okay? Those are the ones that come towards the end of the name of a chemical formula. Okay. So let's look at this one again. Since we've lost an electron and sodium became more positive, we want to know what the oxidation number is of this atom. And the oxidation number of this ion, I apologize, the oxidation number of this ion is positive 1. Positive 1 because it lost that electron. You'll notice that the oxidation number of the sodium atom in its neutral state is 0 because it's neutral. It has an equal number of protons to electrons. Okay, so electron dot symbols, okay, also known as Lewis dot structures, it basically shows the number of electrons around the atom. So in this case, we start with the symbol, which is sodium. It has one valence electron, so we put one valence electron next to it. It lost that valence electron, so we can no longer show that valence electron, but we have to indicate that it is now positive in charge. So let's say we had a different chemical compound. Let's actually go to table. Should do the P table. All right. So we just did sodium right here. Let's pick another one. So we did sodium, and we said sodium was Na with one valence electron. You'll notice it's in group 1. We're going to pick something from group 2. Let's do magnesium. Okay. So magnesium's in group 2, and you're going to write capital M, lowercase g, and it's going to have 2 valence electrons. 1, 2. Okay. You notice that I purposely put that valence electron, okay, in a different spot, right? So I want show when you put your electrons, you want to put them as 1, 2, 3, 4. So this is starting off. You always want to follow the same pattern so you don't mess up. So it's going to be 1, 2, 3, 4, and then you would do 5, 6, 7, 8, right? And that whole goal is to create this T shape. Okay? You want to create the T shape because when atoms start bonding together, they're going to either bond on this end, on this end, so different ends of your atom. Okay. All right, so here we have magnesium, group 2. You'll notice we have 2 valence electrons. I'm hoping this is triggering some of that chapter 3 or in chapter 5 discussions that we had. Okay, and we're going to skip all of these transitional metals. Okay, we're skipping the transitional metals. This is the D block. Okay, for the transitional metals, this was the S block. Okay, and we're going to go to the P block. Okay, and here we have group 13, also known as group 3A. So let's go ahead and do aluminum, right? You could do any of them in group A, but we're going to do aluminum, capital A, lowercase l, and it's going to have 3 valence electrons. So I'm going to have 1, 2, 3 valence electrons in it. Now I'm going to go into group 14, or also known as group 4A. Okay, and let's do germanium, Ge. So germanium, capital G, lowercase e, and it's going to have 1, 2, 3, 4 valence electrons. Right. So I hope you guys are kind of understanding the drift here. Okay, so let's go into group 15. And you know what? Because we already have P for the P group, let's just do phosphorus. It just kind of goes with the flow. So we're going to do phosphorus with the P. And it's going to have, you guessed it, 5 valence electrons. So we're going to have 1, 2, 3, 4, 5. Okay. Now that we've gotten here, we could tell something is different from the other ones, right? So let's think back about our lecture. What is different? What's different is that now this group right here is bonded together, okay? Those 2 electrons are connected together. And until we go into exceptions of the rules, which we won't, general chem will, we're going to leave them like that and bonding. And phosphorus, in this case, will only be able to bond 1, 2, 3 times. So it can bond 1, 2, and 3 times, right? While germanium could bond 1, 2, 3, 4. Aluminum could also bond 1, 2, 3 times, right? So looking at aluminum and phosphorus now, they both could bond 3 times. 1, 2, 3, 1, 2, 3. So why do they have a different charge? Why is it that aluminum, which is in the same area as phosphorus, is going to make a positive charge, while phosphorus is going to make a negative charge? Right? So in this case, aluminum is a metal, right? Here's our metal area. And metals tend to lose electrons. Non-metals tend to gain electrons. So, okay, let's see if I can get my little clicker. Okay. So you'll notice here, right, these different color area right here. This is called your metalloids, right? Metalloids. So metalloids are the ones that act as both metals and non-metals. They have shared characteristics with them. And then you're just going to have your metals. So if I want to just do metals, okay, you'll notice that most of the periodic table is actually metals, and very little of the periodic table is a non-metal. So these non-metals that you see here are going to be your anions. They're going to be the ones that are going to gain electrons. Okay, they're going to gain those electrons. because it's easier for them to gain than it is for them to lose. They're also more, I hope you guys remember the word, electronegative, right? So they have the ability to attract electrons towards them, right? That's electronegativity, the ability to attract electrons. Do you remember which one was the first one? Fluorine. Not the first one, but the most electronegative is fluorine. Okay. Now there's actually a reason for that. Please watch the video again for like the full how and whys of the periodic table that we did. That it has to do with the nucleus, right, and that effective nuclear charge. All right. So now we've gone over the Lewis structures. Let's go back to our lab course. Okay. So we went over the Lewis structures, also known as the electron dot symbol. Okay. And then looking at our views of what the atom looks like, okay, we now remember that metals lose electrons and non-metals gain electrons, right? And actually, let's go back here really quick. Okay. So why is that? Um, just a simple way, we could go deep into an explanation, but I just want you guys to remember a little trick, is that it's easier for aluminum to lose 1, 2, 3 electrons and get a positive 3 charge, but phosphorus has 1, 2, 3, 4, 5 electrons, and this one's already bonded, right? So it's going to be a lot harder for it to do. Remember, it's about the octet. Octet has 8, right? So are you really going to try to lose 5 electrons to get to 8? To get to your lower energy shell? That doesn't really make sense when you could easily just gain 3 electrons. That's um, that's the way I think about it. Okay. Um, all right. Electron configurations. Please watch the video again on electron configurations that we did in chapter 4 to go over it, because that's a little bit more detailed. All right. Oxidation numbers is basically the amount of electrons that you've gained or lost. It's going to be that charge that you get from it. Okay. Remember that when your atom is neutral, you're going to have an oxidation number of 0. Okay, you're going to have an oxidation number of 0. Okay. Now, what happens to the name ending? So a cation stays the same in its name, while an anion changes its ending to "ide." I believe we did this in chapter 5, a little bit of the name ending. Okay. Let's go ahead now and look at this one. Okay, so this is going to be an anion. Anion means that it has gained electrons. So an oxygen atom versus an oxide atom. Okay, you'll notice the difference in the name. It now ends in "ide." Okay, it's not going to be oxygen ion like it was for the cation. It's going to be an oxide ion, right? So what happens here is oxygen, if we look at its electron dot symbol, has 2, 4, 6 valence electrons. Okay, so it has 6 valence electrons. And of those 6 valence electrons, is it going to lose 6 to get to 8 in its lower energy shell? Or is it just going to gain 2? What's easier? Well, it's easier for it to gain 2 valence electrons, and that's exactly what it's going to do. It's going to gain 2 electrons. So here is our normal atom of oxygen, okay? And in our normal atom of oxygen, it's going to gain those 2 electrons. They're going to come on board, right? And what's going to end up happening as it gains those, it's going to go from 8 total electrons to 10 total electrons. You'll notice that now you have 8 positives but 10 negatives. So you're going to be left with a negative 2 charge. Okay? With that negative 2 charge, you're going to represent that in your electron dot symbol. You're also going to write how many electrons you have. Now you're going to notice on this one, the electron dots are just spread about anywhere they want in this. That's I believe that's only because it's harder to do, but it shouldn't be like that. You should follow this example and the one that I'm telling you. So you're going to have oxygen, and it's going to be 1, 2, 3, 4, 5, 6. You could put it right here as well. It doesn't really matter what side I get asked. It doesn't matter. Okay. As long as you keep this T-like shape. So you have 6, and then it gained 2, 7, 8. You want to keep them together. Don't spread them out like this one did. Okay. And then because you gain 2, you're going to have a -2 charge. Okay. So the difference between these is I can make that T-like shape. And you guys are going, why are you on and off in this T-like shape? Because of bonding, right? When you start bonding, it's very, very important to have those electrons in the correct spot. And also, we're going to look at that later in this um, lab, okay? Okay. Everything else is the same. You'll notice that the size of your ion is bigger, okay? Not exactly smaller, but it's bigger. And we want to know, well, why is our ion a little bit bigger? Okay, well, we did add 2 electrons to its outer shell, right? That means that the pull, the electromagnetic pull that the protons have on the electrons, right? We didn't add more protons, so it's not stronger by any means. Okay? It's not stronger. It doesn't have that much of the pull anymore. And electrons like to spread apart, right? So they're going to actually be pushing out, trying to expand that cloud as much as they can, right? So they're not closer together. And that's because electrons, same charge, repel each other. Clear the screen. Okay. Ionic compound formulas. Okay, so in creating our formulas, we want to see how everything kind of combines together to create those formulas. We've already did some of this, but recapping, in this case, they're showing the sodium and the oxygen because that's the examples that we used, right? And so when we are, oops, I don't know what I clicked. Sorry. All right, there we go. I'm trying to find, here are the pen. Sorry. All right, so when we combine things together, remember we had a sodium metal and it had 1 electron, 1 valence electron. And then we're going to have an oxygen metal and it's going to have 6 valence electrons. Okay, we want to know, well, what's going to happen? Well, this sodium only has 1 valence and it's going to be easier for it to give away its electrons. So this electron is going to leave and it's going to pair up with this lonely electron there. So now we're going to be left with this transitional state of sodium with a +1 charge. And it's going to be very, very connected to this oxygen. Okay. Now, this was a transfer, not a sharing of electrons. So what that means is that they're not going to be connected per se together, right? They're only connected through an electrostatic force, so a force of attraction. And it's a huge force of attraction, right? Like magnets put together, okay? That's how they're connected, like magnets. Um, when you transfer electrons, it's like sewing, not transfer. When you share electrons, it's like sewing electrons together, the atoms together. They're actually combined. But when you transfer electrons, they're not combined like this. They're together like this through some form of attraction, right? So you could easily disconnect them and connect them. While when you're sharing electrons, they're bonded, right? So what we have now is this attraction occurring, and oxygen now has a -1 charge. Okay. Now we don't really see that because it's unstable. So what ends up happening is that now another sodium is going to come, and all of this happens extremely fast. It doesn't take its sweet time and do one by one like we're doing it. They all happen around the same time. okay, is this oxygen's going to come. This sodium's going to come, and its valence electron is going to be attracted to oxygen because oxygen is more electronegative. So the electron's going to leave sodium and go to oxygen. And we're going to end up with that same thing. Okay, so this was state 1. Now we have state 2. And we're going to have the final transition here, 3, in which we're going to have sodium, the plus, and sodium. Actually, oops, no. All right, well, rewrite it. So we had sodium, and we're going to just do stage 3, so you guys kind of get it. With the plus here, and we had our oxygen, all right? 1, 2, 3, 4, 5, 6. And we had that electron that went in here, and then we had the other electron that went in there. So we had the other sodium with its positive here. And then oxygen is going to have a -2 charge. These atoms, like I said, are going to be attracted to oxygen. Okay? They're connected to it. They're attracted through some sort of force, electrostatic force here. Okay? There's the attraction, okay, to that more negative, electronegative atom. So they're connected together in that way. You notice that we needed 2 sodiums, 2 of them, in order to fill the needs of oxygen and for them to have a shared octet. And we're going to look at that shared octet. We have 2 right here, so that's a bond. 2, 4, 6, 8. There is 8 valence electrons in oxygen, so that fills its octet. And sodium, okay, that gave away its electron, is very happy right now. It's living off of its other energy shell. So it has 8 valence electrons, 6, 7, 8. So we look at these through its ion. Energy shell number 2 has 8. It's very happy, plus it has a positive charge. So it's just going to hang out now with oxygen, right? Because it's attracted to oxygen. So it's satisfied with its 8 valence electrons in its lower energy level, and it now has an attraction to oxygen, okay? And that's what creates this lovely bond that we see. The oxidation states of each, so you're going to have sodium has an oxidation state of +1 and oxygen has an oxidation state of -2. We're going to have 2 sodiums for 1 oxygen. Erase. You see? All right. So this part right here, valence electrons, ionic charge, and the periodic table, that's kind of what I already showed you guys when we were looking at the periodic table here as our lovely little mess, right? So let's clear that. If we recall, group 1 makes 1 charge, group 2 makes a +2 charge, group 3 +3, group 4 ±4, and all of these are going to be negative charges. And is it going to be a -5, -6, -7? No, it's not, right? So how do we know what charge it's going to be? Well, remember phosphorus, 1, 2, 3, 4, 5, right? It can make 1, 2, 3. It can gain 3 electrons, giving it a -3 charge, right? So 15 plus 3 negative electrons, or sorry, not 15, let's do 5. 5 plus 3 is going to be 8, and that's going to be your octet, so you're going to gain those 8. 6 plus 2 is going to be 8, right? And that's going to give you your octet. 7 and 1 is 8, and that's going to give you your octet. So I'm trying to delete this number here so you don't get confused, right? 8 plus 0 is going to give you that octet, right? So these are your noble gases. Your noble gases do not gain or lose electrons. There is a few exceptions to those, but now with new discoveries that have been made. Yet in our case, they're not going to bond. They are inert. Noble gases do not react. Okay. The reactive nonmetals are these groups right here. Okay, the ones that you see right in front of you. Those are the most reactive nonmetals. So they're going to combine with everything because they're very electronegative. Okay, and remember, they gain electrons. They don't lose electrons. Right. So if you're in group 15 or 5A, you're going to gain 3. If you're in group 6, you're going to gain 2. And if you're in group 7, you're going to gain 1. All right, so the next part is going to be with naming, and when it comes to naming, how it ends and what do we do with it, right? So we know that a cation, positive, it's just the name of the metal plus the word ion. However, an anion, it's going to change into ide. So bromine is going to be bromide, right? So here is bromine, right? And that is actually going to turn into bromide, right? So you're going to change the N to ide, right? Like the little Ozzy Osbourne song, ide. All right. So you're going to change that ending into I. That's it. Quite simple. If you look at the charges aren't, they do play a role in the naming. So let's actually show you guys a quick way to create a chemical formula. All right, here is calcium, and calcium can make a positive 2 charge, and bromine. Are we using calcium? Yeah. And bromine itself, though, is in group 7 right here. So it could only gain 1 electron, which that means is that it can only make a negative 1 charge. So you're going to need 2 bromines, right, to counter this 1 calcium, because calcium can have 2 charges. You could go ahead and draw the atomic model the way that we did. So where we are like, all right, here's calcium, okay, and calcium is going to have those 2 empty spots because it's going to, here it is. There's calcium. Bromine has 1, 2, 3, 4, 5, 6, 7. And you could show this and go, all right, this is going to come here. So now we have calcium, and it's going to have a +1, and it's connected to this bromine, which has a total of 8 and a -1 charge. But you're like, all right, but calcium still has 1 electron in it. So, sorry, I forgot the R in bromine right here. Let's give it an R and 2 extra right here. Let's just turn that into an R and okay. So another bromine is going to come now with its 1, 2, 3, 4, 5, 6, 7. Okay, you'll notice that I just did them a little bit differently. Okay, I still have my T-like shape, and I'm going to show that this one is going to come right here and bond with that one. So now I have calcium with a +2, and it's going to be connected to bromine. And each bromine now has a filled octet with a -1 charge. I did it again. All right. So you could do that for each one, and you're going to realize that it's going to take you a very, very long time as the molecules get more complex to go, oh, I need 2 bromines for every 1 calcium. Okay. But what happens when you get more complex models, or you want to just do it really, really fast, and you don't have the time to do this? Okay. There's going to be something that I like to call the crisscross method. Okay. So the crisscross method is a lot simpler for me. Okay, you're going to have the numbers that are related to the charge, and you're just going to cross them over. like that. So not the charge itself, just the number. So we're going to have calcium, and there's one of them, and bromine, and there's two of those, okay, because you're going to cross that over. Now, we don't really write calcium 1, bromine 2. You're going to write it as calcium and and it's not bromine, it's bromide, calcium bromide, okay. I put the 1 here just to show you guys that crisscross thing. You don't have to do that. Just directly don't write it because we already know there's 1, and just go straight to this. Save yourself some time, right? So the 1 comes down and the 2 comes out. That's called the crisscross method that allows you to easily create your chemical formulas. All right, what if we have charges? So metals with charges. These ones right here are from our transitional metals. Okay, transitional metals can have more than one charge. Okay, they have more than one charge, which means they have multiple oxidation states, and we have to be able to show those multiple oxidation states. So we have 2 examples. The first one is going to be iron. We're going to take a look at this one. Now, in iron, we have iron with a +2 charge, and we have iron with a +3 charge. Okay, so ferrous and ferric. So both of these are going to be the word iron because they're cations, right? So you're just going to give it its normal name, iron. And in parentheses, you're going to put the Roman numeral of the charge that it has. So in this case, iron 2+, so you're going to have iron Roman numeral 2. And this is all connected. It's all one thing. And then ion. That's it. Iron, Roman numeral 3, and then ion. Okay. So when you write your compounds down, you already know what the charge is. So let's do this one. Okay. So Fe, and then look, we know it's a +2. And then we'll do it in case, let's pretend we don't know what the charge is, right, with the -1 charge. So we have this one, so we're just going to crisscross, right? If we remember, we're going to bring the 2 down, and this is a 1, so we bring the 1 down. So this is just going to be iron bromide, okay, with the 2 down. And that's how you would write it. So this is assuming we knew the charge. Now let's pretend we don't know the charge. So let's do this one right here, iron without the charge. So, and we have to figure it out. So we're going to do this one right here. Let's say we're going to go reverse and we're going to create the name. We're going to create iron bromide as our name. So we have this, FeBr3. And it wants you to write the name. And you're like, I don't know which iron it is. Is it a +2? Is it a +3? Is it the +4 one? Right? Well, we're going to use reverse crisscross method. And what that means is you're going to take this 3 and bring it up. And you'll notice there's no number there. That's the same as a 1. So you're going to bring that up. So now you know you're going to have iron 3 as your charge. So you're going to write iron, parentheses, Roman numeral 3, 1, 2, 3, and then bromide. Okay, we dropped the word ion. I don't know if you guys noticed that we didn't say iron 3 ion bromide, right? It's just iron 3 bromide. That's it. So whenever you're stuck and you have a chemical formula and you want the name, just do the reverse process in order to get the oxidation state from that reverse process. Now there is some that have some transitional metals that have fixed charges. There's not that many of them, so it's quite easy to memorize which ones have the fixed charges. So this one's talking about the ones that have fixed charges. In this case, zinc, silver, and cadmium have a fixed charge. That means that charge is not going to change. It's not multiple, so you do not use Roman numerals. Okay, so zinc, silver, cadmium, don't use Roman numerals. It's just zinc ion, silver ion, and cadmium ion. the best way to do this one is just memorize the charge or look it up if you're allowed to look it up. Look it up, right? So zinc makes a +2, silver makes a +1, and cadmium makes a +2. If you're never sure, look at what it's combined with and do that reverse crisscross method, and you can figure out what the oxidation state is that way. Polyatomic ions, remember those are atoms that are combined together with a charge posed to them. Also, same thing is looking them up, unless you want to go ahead and figure each out by drawing it and finding the formula charge and figuring out, well, what's the charge of this? What's the charge of that? Okay. You could just look a chart up of polyatomic ions and bring those together. Okay. One of the things that this doesn't mention that I should mention is that these names that we saw here, the names we see here, then any kind of name, right? Uh, it labels it as compound name, but it's also known as the IUPAC name. IUPAC. So if you ever see what is the IUPAC, right? IUPAC. That's just a fancy name of saying the compound name. The other fancy way of saying it is nomenclature. And I actually like that word a lot, nomenclature. Because you don't get to use something like that often. Nomenclature. Sorry, I'm trying to write it small so I can say. Okay. Nomenclature, what does that mean? It just means naming. Naming your compounds, the names of your compounds. What is the nomenclature of this compound? Well, you're going to be like, okay, it's iron bromide, right? What is the IUPAC name of this compound? Oh, it's iron bromide. When you say it, you're not going to say iron 2 bromide. You could. It's just iron bromide, right? If it indicates it wants, like when you say it out loud. But when you write it, you do have to indicate it. So remember, the word nomenclature and the word IUPAC just mean compound name. They both mean compound name. So don't freak out if you see those. Just means compound name. That's it. What is the IUPAC? You're like, what? Compound name. What is the nomenclature? Compound name. Okay. All right. So we were leaving off right here. So with this one, common polyatomic ions, just you have to remember their name, and also remember that they are a group. Okay. These are grouped together. So you might see ammonium oxide or hydroxide like this. This is one group and that's one group. You could group polyatomic ions together. These are two polyatomic ions, right? Ammonium hydroxide, right? Hydroxide is actually a base, so this is now a base. That name we just created right there. Okay. You could see ammonium nitrate, calcium nitrate. You could see magnesium chlorite, magnesium hypochlorite, right? So all of these, I just suggest you print out a common polyatomic ions name, have that ready for your quizzes and your exams and everything that you might do. Because it's very handy, I would actually just print this page out because it's kind of nice. Okay. And when you are naming it, just like I did, it was like you would say calcium phosphate, right? Sodium sulfate or sodium sulfite. Okay, you'll notice that the big difference is the amount of oxygens that you have. If you ate more oxygens, you're in 8. So you have more oxygens, you ate more of them, you're in 8. Yum, yum, yum. So here you have 4 oxygens. Here you have 3 oxygens. So you didn't eat as many oxygens, so you're all right, right? Like, you full? Nah, I might. I ate enough, you know. And this one, oh nah, he ate. That sulfur ate. It ate a lot of oxygen. All right, that's basically how I remember it. Is one of them ate more than the other? Okay. The other one is just all right. Okay. Da, 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 da. All right, so now we're going to go into the structures one, and creating our structures and our molecular compounds. They're going to have a lot of different structures. This is where putting your electrons in its proper spot for bonding actually comes in place. Okay. And what I'm going to do is actually I'm going to make a separate video for this section here, the molecular compounds. All right. So I'm going to stop this one right here and make a separate video so that way you guys could just focus on molecular compounds on their own. You guys, I'll see you soon. Ciao.